shall we start?
Recording.
Okay, so good afternoon, everybody, or good night, maybe, for those in Europe. Good afternoon for those here in South America or in America. So it's a pleasure to be here this afternoon with all of you. And especially in the first talk, we have Professor Karl Kunish from University of Graz and the Academy of Science in Austria, Hadon Institute. Professor Kunish is an expert in control, optimal control, and several other things in analysis of PDEs. So it's a real pleasure. He's a prolific mathematician. He is the editor of several journals, including Scion, COCV, Scion Analysis, Journal European Mathematical Society. So just a few of important journals that he has been in the editorial board. And also he has directed many PhD theses, many papers. So it's a real pleasure, Professor, to have you here this afternoon with us and hopefully soon in person. Okay, so it's up to you now.
Oh, thank you very much for this kind introduction. It's really an honor and a pleasure to address you. I congratulate you on this activity because after all, I mean, these internet talks, seminars, meetings, in some sense complicated, but you have such an elite group of audience and speakers that it's really successful. I'm going to talk on a topic which has been mentioned in several previous talks, namely solving the Hamilton Jacobi Bellman equation, which arises in optimal control. I have really the pleasure that I have been supported by quite a few postdocs who are now professors at diverse institutions. And I really needed their help in analysis and also in numerical realization of this topic, which I am going to address when I speak on an optimal control problem subject to a dynamical system with a control, BU, acting on the system. And to be specific, really, it is a stabilization problem because F at the origin is 0, the running cost at the origin is 0. So the origin is a solution to this problem, but it's not necessarily a stable solution. So we want to stabilize. And one way of stabilization is by means of optimal control. We want to do it in feedback form, and feedback evolves around the value function. The value function V of X, which associates to the initial condition of this dynamical system, the value of the cost as a function of X. And it is well known, or it can be done, at least in the case that V is smooth, with relatively little work, to check that V satisfies this equation, which has the additional feature that before it's really an equation, we have to minimize with respect to U in the control set. Okay, the unknown here is V, the gradient of V, and it has this V also satisfies boundary conditions. V at 0 is of course 0. V is non-negative and it's 0 at 0. So it also has the property that the gradient of the origin vanishes. Of course, in general, the solution is not smooth, so we ought to address viscosity solutions, we ought to address issues like quasi-convexity and many other issues, but I want to come to a different focus very soon. Just let us note that in case UAD is the whole space, in case we have an unconstrained problem, we can do the minimization of this quadratic functional with respect to U by hand, and we find the optimal U star of X is the B transpose gradient V. And we can split this U star into the equation, and we arrive at this hyperbolic equation for the V in the unknown X. It's nonlinear because of the quadratic term here. It's hyperbolic, and its dimension is in the state space of the ordinary differential equation. If it's ordinary, if it's a dynamic system for a PDE, then it's operator theoretic HGB equation. Let's assume for a moment that we can compute V or gradient V. We can take it, stick it into the dynamical system, and we can do what's called closing the loop. So if we know gradient V, we have solved our problem. So what's the issue here? What's the difficulty? Well, the difficulty is to get a hand on gradient V. And Bellman in the 60s coined the term of he coined the term curse of dimensionality at this moment. He said, what casts the pall of our victory? It's the curse of dimensionality, a malediction that has plagued the centuries from earliest days. Well, he was exaggerating a little bit, maybe, but still, if we remember that this is a hyperbolic equation, if we discretize it over a grid of dimension n with n nodes in dimension Rd, then we have to solve a nonlinear problem in n to the d, an exponential number of variables, plus the minimization. So this is the issue that I want to address without too many technicalities indeed, but I want to maybe explain concepts which one can utilize to get a hand on the HGB equation. So a list of techniques, not complete, I must say, a list of techniques which are available. Of course, you can try to solve the hyperbolic equation directly, but after a certain dimension, maybe 6 or 7, it's over. Policy iteration is a fairly old technique, but it has to be combined with new technology to make it successful. There are data-driven techniques, there are learning techniques, and I always mention some names who have contributed. And on these techniques which are expressed in red here, I will talk later on. Then there's Taylor expansion, Hopf formulas, which are very elegant, but restrictive because for many important problems, Hopf formulas are not available. Max algebra is a very clever technique, but it is also plagued by the curse of dimensionality, tree structures, and so on. One question which arises early along is Hamilton Jacobi Bellman really worth the effort in view of the fact that we could linearize the nonlinear equation? Then maybe the cost is quadratic. We have a linear quadratic problem. Riccati equation is a technique to solve this closed loop problem. So why don't we always just utilize linearization? The answer is because it is local. Not only are the theoretical results only guaranteeing the success locally, but it is also possible to find actually quite simple examples where the locality is predominant. So there is an issue here, and we need to step forward. There's another issue here, which I shall not address, but I want to point it out. We are assuming for this closing of the loop that we have observations. We have observations of the state. If these observations are not available, we have to construct observers. We have to construct nonlinear observers. And in doing that, again, Hamilton Jacobi Bellman equations arise. So the point I'm making here is HGB equations are not only important in the context of optimal control, but they're also important for observers in game theory, etc. All right. I want to come to policy iteration first. And rather than talking too much theory, I want to explain an example. Policy iteration, in essence, is a linearization, builds upon the linearization of the nonlinear HGB equation. I want to show you an example in very high dimensions in a moment. Actually, I start out with an infinite dimensional problem for closed loop control of Fokker-Planck. Fokker-Planck involves this parabolic equation with I make it on a bounded domain. So I have a variational boundary condition, initial condition. The control appears in the potential here, in this function V, which is a summand of base potential W and a control potential. And it is known that with the control, without control, the system converges to the stationary distribution, the Boltzmann distribution. But this convergence is very slow, and it's characterized by the energy in the ground potential W, corresponding to potential wells, and to the viscosity nu. And the rate is exponentially slow. So controlling, optimizing this convergence to steady state, to the stationary distribution, is of significance in applications. As an aside, as a comment, I want to say, not only is it of importance to optimize U, but it would also be interesting to characterize the best possible alphas, which really are the location of where and how the laser acts onto the system. But that's a different topic, which is of importance. For the moment, I shift towards the origin by introducing Y, and then I arrive at this bilinear optimal control problem in this format. And on top of, I want to stabilize now, and on top of it, I'm going, this is the optimal control problem here, and I want to stabilize with a quadratic function. In the situation where the ground potential, the confining potential is this, and then it's known that the stationary solution has its maxima where the confining potential has its minima. So we are not surprised that the stationary distribution looks something like this. As I said, I want to do this by policy iteration, simply by Newton. And the linearized equation have a norm, have a name in this context. They are called generalized HGB equation. Why generalized? I don't really know, because I think they are just linearized equations, but that's the terminology in the engineering community. So what I want to do here in this layman's movie, which I show you next, is we initialize at the beginning, all our particles are concentrated near 4, and we want, as the trajectory evolves, we want to reach the steady state in black. And here we go as time evolves. In red, you see the uncontrolled solution. In blue, you see the solution obtained by feedback. Now, how do we still have the infinite dimensional Fokker-Planck equation, which needs to be discretized. And again, against what I do usually, use spectral elements for discretization. Here, to just show you high dimension, we discretized by finite elements. We took the Fokker-Planck equation, we used 1,000 elements, and we have a 1,000 dimensional ODE as a boundary condition. Okay, and the weight of the control is this. So we really have high dimensions. All right, and now time involves, I let time run. As time is 12, okay, the blue one, the optimally controlled one, is almost there. The red one is still struggling to get to steady state. All right. Some words about the ingredients of policy iteration. Some comments of how to make it work. First, if the constraint is really a PDE, in general, use some mesh-free discretization. Number one. Please, let's exploit as much as possible separability properties of the right-hand side. Then we do a Galerkin approximation of the linearized Hamilton Jacobi Bellman equation by basis functions which are globally supported, like monomials, Legendre polynomials. So I'm approximating in a linear expansion. And the next thing I see, if I do Galerkin, of course, we have high-dimensional integrals. So let's exploit separability as much as possible, and let's also take the answers function in a separable structure. As soon as I do this, I have how many? Okay, what's the number of unknowns? If I have a linear system in order D and I take basis functions, then I would have n to the t unknown, so I'm back at the curse of dimensionality. But now tensor train, the tensor structure, and by tensor train technology, we can significantly reduce the number of unknowns to reach an error level epsilon. We have to choose how many unknowns. We have the tensor train dimension R to have an overall number of unknowns which are by no means exponentially high anymore. Of course, if we build everything on tensor trains, then also the discretization has to be done that, and the linear scheme has to abide, has to follow this tensor train decomposition, which I don't go into now, but I want to say, just simply say here, there is a technology how we can solve our equations by the alternating linear scheme, which preserves the tensor train structure. So this, by all means, is one possibility to proceed. Another one, and I am completely changing focus now with respect to technology. The problem is still the same, namely get a handle on HGB equations by a data-driven approach. This is just the modern name of what we would have called interpolation in the old days. So you take ND initial conditions and you create the value function, maybe by open loop solves. You solve the optimization problem with these type of initial conditions. Then you get data. And now you want to interpolate, for example, by a polynomial model. So the unknowns become theta, the expansion coefficients, theta I. Okay. Now I do a regression problem. I have Vj's are the values of the optimal controls, of the optimal value function at the interpolation points xj. I produce the mass matrix, and I have my linear, my quadratic interpolation problem. Plus some penalty term. And also, as already was pointed out in the first two lectures on Monday, there is many times, in spite of the fact that this is that we are addressing high-dimensional problems, there's the key ingredients are encapsulated in lower dimensional information. So really, in this case, this means only a few of the theta I parameters contribute significantly to the solution of the value function. And for this purpose, we use sparsity type of regularization. An L1 term of the vector of the theta i's. L1 is such a sparsity enhancing regularization term, which is of tremendous importance and power here. The L1, for those who have not worked with L1 regularization, this means that the optimist, at the optimum, really not only some of the coefficients are very small, but note, the minimizers have the properties that the unimportant coefficients, coordinates are really identically zero. And this you can convince yourself by a very simple problem. You get a one-dimensional problem, a quadratic cost, and a linear, an L1 type cost, and you see that in certain cases, the solution is just zero. Once we have solved this, data-driven approach, or once we have solved the linear regression, the quadratic regression problem, we have the coefficients theta I, we can build V theta, we stick it in, we do our arc minimization, and we get the feedback, which we use. Well, this is not the end of the story for making it practically powerful. Really, what we do is we use gradient enriched data, which is to say that at the data points xj, I not only compute the value function, but also its gradient. And the rest is the same. We have to enrich our mass matrices here, but this is known. We have to solve this similar type problem. And this is a very important aspect in making this successful, to enrich by the gradients. All right. Now you may say this is very expensive because I need my gradients. No, in any way, if we compute V by open loop solves, then the dynamical program is based on the adjoint equation. So we anyway, to solve such problems at a specific data point, at a specific initial condition, we solve the primal equation, the adjoint equation on the infinite horizon, and we have the coupling between adjoint and U. And once we solve this, we know that the gradient at the point X is just P at zero. So this is very doable. And we have many examples where we made this work. One more important point. If I explain to you that we are, again, discretizing by, in this case, polynomial ansatz, and I want to address, again, we are using separable structure. The focus now goes on the exponents of these one-dimensional objects. We can choose them in such a way that we take the sum, the L infinity norm of the powers less than the order of the polynomial. Then, this is a quick way of looking at it. Then we are back at the Cursor dimensionality. We can take the L1 norm of the coefficients less than S and call this the order of the basis function. Then it's a total degree, and the complexity is only polynomial anymore. Or we use the hyperbolic cross, which means we use the product of the exponents. Plus one, this is taking care of the constant functions. Then we have really a very low dimensional approximation. This is referred to as the hyperbolic cross. And it works very, very surprisingly well. Well, you may say maybe the regularity of the value function comes in. It does to some degree. For the purpose of time, I don't show you too many, I don't show examples, but rather make the important remarks on this. The question is sampling. We use Hamilton quasi-uniform sampling. I want to address the issue that gradient augmentation is essential. I want to stress that sparsity is really essential. We get rid with very lower number. Hyperbolic cos together with L1 sparsification really allows us to get good results and prove sometimes also convergence in certain situations with very few degrees of freedom. Of course, we are building our function by choosing sample points, but we need to validate. We never forget to validate, of course. The influence of the regularity of V comes in an important manner. Then we have addressed the issue of convergence as the dimension of the approximation goes to infinity. We have addressed the situation where V is not C1, but we just do a approximation, Yoshida approximation or whatever. And of course, the question also arises, is it of interest not only to augment by gradients, but also maybe by Riccati equations? This is an interesting issue. I come to my third topic, which is another technique of how to partially alleviate the curse of dimensionality. I repeat the problem under consideration. I want the feedback for all y0 in a bounded set. So that's what we do. For the moment, I assume that V is in C11. Please note where the control enters, quadratically in the cost, linearly in the constraint. But really U, we are looking for a U which has the form which I indicate in red here. So I'm going in this learning scheme, I'm to say I am replacing the value function, I am replacing this term up here with a function V, which I don't know. I want to approximate the whole function. Okay, so here it is. And first I minimize over all C11 functions which satisfy the boundary. And this is a very complicated looking optimization problem. In addition, I have very little information for that because I look for a function V on the domain omega only along at one trajectory, only one initial condition. Of course, we are not only evaluating on the initial condition, Bellman principle comes in, okay, etc., so that we really can interpret this as learning along the whole trajectory. But still, if this trajectory is not space-filling, it's very scarce in space, we want to have more information. So I take my initial conditions in a subset little omega. I endow little omega with a measure, a Lebesgue measure or a point measure or whatever measure, skew measure, what you wish. And then we take this as the learning, as the averaged learning scheme. We minimize this functional. We have to average over all of that, subject to this constraint here. That's the averaged learning approach, which we have studied very deeply over the last years. What are some further ingredients of that? Well, when we first worked on this, of course, this is the time where one cannot avoid neural networks completely. I mean, we were also trying to, of course, work with neural networks, and we implemented them. One of the colleagues whose name was on the first slide, Daniel Walter, he worked very hard to make the neural network approach working. And when it finally worked and we proved its convergence, we had because I said, well, but why don't we again try with polynomials? And when we tried with polynomials, and I should say at least algorithmically, we were more successful. Maybe I stress we, okay? Maybe somebody else can do better with neural networks. And then again, we do the approximation, and then again, we do an L1 type combined with an A2 type sparsifying. Additionally, there's one more thing. We don't minimize these things over the whole time horizon. This is very impractical. Everybody computes, knows that over the infinite time horizon, we cannot. So to be serious, we have to take into consideration the fact that we can only work over a finite time horizon. So when it comes to addressing convergence, there are many issues which we need to take into consideration. I just mentioned finite time horizon, discretizing the value function, and approximating possibly a PDE in the background by a node. I should just say that we have done that without going into detail. First of all, these learning schemes allow optimal solutions. Secondly, as time goes to infinity, if the regularization parameters go to zero, if the cardinality of the approximation goes to infinity, and the theta k's are chosen as the solution, then we have convergence of the value function as you like, as we expect. Very nice. For the polynomials, this is sort of simple. No, this is doable. But we had a really hard time for the neural networks, I at least had, because the universal approximation theorems are generally stated in the space of continuous functions without constraints. But we need to work sometimes with Sobolev spaces or CV1. So I had to sort of generalize the universal approximation theorems to this situation. Okay, so far, this is also true without the CV1 property, by the way. Now we really need, at the moment at least, the CV1 property if we want to also get the optimal controls we obtain in this manner to converge, at least weakly. It's still an open issue whether we can push to the limit here. Yes, we can push to the limit and get some object, but whether it's of the type B transpose gradient V bar of the solution, that's still an issue. The convergence is, we have made progress, but we are still working on it. All right, important remarks in this situation. First, when one goes to the computer, of course, one compares whether everything is consistent with Riccati based in the linear quadratic case. Next one, we can prove results. We can prove results for the situation. We can prove results in the situation where we have our data, but it should also work if we apply the feedback to initial conditions outside for the training points. And this has been addressed basically by means of, well, Bellman's principle and Grunwald inequalities. We have seen that we need to evaluate the value function at the gradient also in this approach, and for optimality conditions, the Hessian. This can be done well with graph theoretic techniques. Now this is an interesting, second to the last point. The optimality condition for both the data-driven and the averaging approach, from the point of view of the optimality condition, the two approaches are not so different. That's interesting. And then, of course, the question arises, among all these things, what works best? Well, we are far from knowing that, and especially we don't know for very high dimensional problems. But we wanted to know at least for low dimensional problems. And then we looked into the literature for nice test cases for nonlinear problems. And this is not so easy to find, these test cases. And so, of course, in the case of the conical equation, ionical equation on one hand, but this doesn't precisely fit. And then for game theoretic examples, but this doesn't fit to the context. So we produced our own test problem, which looks very simple at first, a quadratic cost with a very linear, simple constraint. And then we said, okay, let's make the cost different. Okay, we add a penalty to the cost, and the penalty to the cost in 2 dimensions, this is our state space, 1, 1, 2, is basically a big smooth hat with support inside this circle. So it's like a constraint, but it's not a strict constraint. It's just a big penalty. It's just a big penalty. Okay. So the trajectories need to avoid as much as possible, depending on the penalty parameter alpha, then they should avoid this region here. We have done tests with this as a function of alpha, and roughly speaking, the tests say, for examples of this type, the data-driven approach does quite well and may be beating the averaging learning approach as long as alpha is small. And alpha becomes large, the learning approach may be the better one. And there are a couple of comments about this value function, corresponding to this example. It's semi-concave, it's Lipschitz continuous. If alpha is small, the penalty is small, then it's C2. If alpha is large, then it's semi-concave, but it's not differentiable. And it has other properties which are nice. It's bounded from above and below by quadratics, it's exponentially stabilizing, etc. So by this, I want to come close to an end. I have explained 3 techniques, and I have shown you one test case, which I think has some potential to be of importance in other situations as well. And with that, okay, yeah, so this is the value function as alpha increases, and you see as I increase, at the beginning, the level sets are smooth, I increase, and you look where my mouse is to the left here. As I increase the alpha, it loses smoothness. And with that, I just summarize, but instead of a proper summary, I just say HGB equation in the context of optimal control will remain a challenge, I suppose, for some time to come. Thank you very much for bearing with me. Thank you very much for your attention. I stop here.
Okay, so thank you very much, Professor Kunish. Now we will open for questions, comments. If anybody wants to ask, I think the mic is open. Otherwise, you can write in the chat. Or you can write it in Portuguese. Vocês podem escrever em português, pessoal. Em espanhol también, si queréis, que lo leemos. Bueno, this was a very, very nice talk, Professor. So, do you have any reference for those young people who wants to start?
Yeah, I have references. Here are the references. I think you asked me for an extended abstract, right?
Yeah.
So on the abstract, you find references to our own papers. And in these papers, we really make an effort to quote many of the colleagues' contributions. I cannot say that we quote everybody, but we made an effort to quote many people.
Oh, thank you.
So there is as well on the talk as in the abstract, there are references.
Okay. So that's it's nice so people can take a look. Ok, so alguma pergunta, pessoal? Pergunta, comentário? So as you said, there are many things to do still in this field, right? So it's good to young people to start working on those things for those who are interested in learning Hamilton Jacob.
Yeah, okay. But you have to have some stamina. But all of the young people have a lot of energy, so it's fantastic. Okay.
Yeah.
Thank you.
Thank you, Professor. So